Okay. Sure. Okay. Good morning, everybody. I got the output chat saying live session is not recorded. Yeah, actually, let me check. Okay, I think it's now released. So the way it works is that for TA lab session, it's not automatically published. It's automatically recorded, but I have to push the button every day. I forgot to do that. I'm very sorry about it. I should have done that last night. Okay, but if you, yeah, so that's my fault. I will try my best not to forget to publish on the night of the lab session so that you can watch it. If not, send me email that I try not to, but if not, send me email to remind me that I have to push the button to publish the lab session. That's the same for the lectures and so on. So usually it takes like 2 hours or so to somehow for Zoom to process the recorded video and then so that I can actually post it. So that time lag is always a tricky thing because I tend to forget. Okay. Right. If you have any question now, I think you guys want to actually ask question chat. So I try to answer the question if you type it in the chat. And then, you know, if somebody else has answer, you can also try to answer in the chat to the question in the chat too. Okay. So do you have any other questions or concern? So far, so good. Okay. So today I'm gonna talk about the first lecture about how to describe the data. Do we answer the quiz after the lecture? Yes. So each lecture slides has its own clicker questions, and then usually I actually go over the answers. But just to make sure that everybody watched the lecture, I constructed the clicker quizzes on the Canvas, as you know, that you are going to answer the quiz after the lecture. I'm not sure if it's a good idea to do it on time, but if it's not too distracting, you can actually do it on time during the lecture. But when you do so, you probably be maybe a little distracted. So it's your choice, but for the quicker question one, we are not able to see the picture graph. Yes, you cannot see it because I just copy and paste my slides without graphs. So those are the questions meant to be answered while you are referring to slides or just after watching the lecture. So whenever you watch the lecture, make sure you have well, you always have to have a pencil to write it up or whatever you see. But especially for clicker question, make sure you're actually gonna write up the answer so that as soon as you finish, you just go to Canvas and finish it up. Is the first assignment based on today's lecture? Yeah, but I think that the first assignment question, many of them is, yes, some of them we are going to cover in the lecture, but also that the lab session should have covered many of the summation stuff. Okay. Yeah, I think that the best way, as you guys say, is that there's a class notes on the summation principle, so that's very useful. Okay. Or you will learn summation today. Yeah. Okay, let's go on then. So first we want to talk about measure of central tendency. So given the data we get, we try to summarize the data somehow. Okay, data contains sometimes many observations, millions of observations in a very big data set. If you think about the data set creating on the website, really literally there are millions of observations sometimes. In other cases where like biology or studying the DNAs and things that that involves many observations. So data, big data is nice, right? We think it's nice to have a big data, but unless you know how to extract the information from the data set, it's useless. Data itself as it is so complex that you just don't know what's going on by just literally looking at the number in the data set. So you have to know how to somehow summarize the data. And then the question is, what type of summary statistics or summary measure we can think of, okay? And then today we're gonna think about the broadly speaking, two different types of measure. One is measures of central tendency. The other is a measure of variability. Okay, so first we're gonna talk about measure of central tendency. I think you are already familiar with some of the words, but here we try to make sure that you understand exactly what those words mean. So there are three central tendency measures we're gonna consider. One is a mean, so it's an arithmetic average, okay? The other is a median. Median is a midpoint of ranked values. And then finally, there's a mode. If the data set, the variable we look at is gonna contain the integer value with relatively small possible number of integer values, then the mode sometimes is useful because mode is the most frequently observed value. Mode is, by the way, not so useful if you are looking at the continuous variables such as, say, I don't know, the height, which is a centimeter, or the weight, which is a kilogram. So they tend to be very different. And then in principle, it could take like a digit number below the digit. So that in such a case, thinking about mode stuff. So let's look at the one by one. So first, arithmetic mean. Probably this is the most familiar measure for you to think about measure of central tendency. Arithmetic mean is the most common measure of central tendency. So I'm going to think about distinction between population and the sample. For now, you keep wondering what is a population, what is a sample. Later, we're going to be a little bit more explicit about this. But population is in principle is something going on in real world if you have all information. So you can think about, say, if you're interested in extracting information about all Canadian households, okay? Actually, the census year, they try to get all the data for everybody in Canada, okay? And then that you have a population of Canadian households, say if you're interested in income of the Canadian household, different household get the different annual income, but in the data set in census year, you have all value about the household income. And then you're gonna take the average across all Canadian households to compute average household income. Okay, so that is an example of this population arithmetic mean. Okay. Sometimes and often because it's very costly and time consuming to survey everybody, okay? Often the data set is created by randomly sample from the population of interest, okay? So for example, except for the house census year, the Statistics Canada often just randomly pick some subset of the Canadian households, say 10,000 Canadian households across all over the Canada, and then ask survey question about how much they earn in this year. Okay, so such a data is more of the typical data set we have if government do a survey, because as doing survey to everybody is very time consuming and costly. Okay, so in that case, you have a sample. Okay, sample of size n here is a lowercase n, which is smaller than the upper letter n, which is all Canadian households, the number of Canadian households. Okay? And then you have the sample, okay? And then you compute the average. That's the average of the sample mean. Okay? We're gonna repeatedly come back to the sample and the population later. And sometimes population of interest have infinitely many possible observations, okay? Because you're gonna think about hypothetical world where you have an underlying distribution with infinitely many potential observation behind, and then you think about drawing a random sample from there. But if you, again, we're gonna come back about the population sample later. So if you don't fully understand that question, don't worry too much about it for now. Okay, so so arithmetic mean. So we wanna think about the advantage and the disadvantage of arithmetic mean as a measure of central tendency. Okay, arithmetic mean is very simple and intuitive because you get used to. Okay. And then the mean computing it is relatively straightforward because you just sum up the value and then divide by the number of values. So if you got, in this example, 5 observations, okay? And then you have a 5 value, and then you sum up those values and then divide it by 5 because you have a 5 observations. That will gives you the arithmetic mean, okay? One disadvantage, I should say, is it is sensitive to the presence of extreme value. Namely, if you have a very extreme value of which value is very different from the rest of the observation, one or two extreme value, which we often call outlier, tend to affect the measure of tendency, which is arithmetic mean here. Okay, so here in example, suppose that you got the 5 observation, 1, 2, 3, 4, 5, and then that mean is going to be 3. You can confirm that sum of 1, 2, 3, 4, 5 is 15 divided by 5, that gives you 3. Okay, so on the right side panel, you have a 5 observation, but one of the observation is very high. Okay, and just having this very high observation gives you a substantially different arithmetic mean because the outlier gives you the impact on the measure of tendency. Okay. So this disadvantage becomes clearer once we're gonna think about the median. Okay, and this is not necessarily a trivial issue actually, because sometimes in the survey data, somebody has mistyped the number so that there's 2 more zeros at the end, so that you got very, very big number for one of the observation, and then compute the mean, and then that value of computed mean is going to be very sensitive to such a mismeasurement. And also that if you think about average income or average wealth, yeah, especially like average wealth, if you think about it, then there's a very handful of people with enormous wealth, so that if you compute the average wealth, the average wealth you're gonna get as a result actually tend to be very big from the viewpoint of the usual household with average income. However, the reason why you tend to get very big wealth, very big average wealth across all people is that there are a relatively small fraction of people with very big, enormous wealth. But if that's the reason why you get the high average wealth, that doesn't necessarily reflect the regular household wealth. Okay, in contrast, median is gonna fix this issue about sensitivity to the extreme value. Okay, so they come back to the same example. Okay, median is gonna be the middle ranked value. So you got the 5 value. Where is the middle point? Middle point is 3. Okay, here, if you think about the other example where you have an extreme value, but the middle point is not going to be sensitive to the outlier. So even if this 10 is going to be like 1,000 or 10,000, it doesn't matter, still you get the same median value. Okay. How do we avoid counting such outlier? Okay, so I have a question. How do we avoid counting such outliers? Well, there's no good way. So the point is that when you have a big data with many observations, you don't, at least initially, you don't necessarily know what is, whether you have outlier or not. So one way to do it is actually compute both median and average. That actually gives you the idea that there is an outlier in a lower end or higher end. If you have an outlier in a higher end, then the mean is going to be bigger than the median, as in this example. Okay, so computing both arithmetic average and the median to compare gives you some idea of the presence of the outlier. Okay. Yeah, interquartile range and so on is something we're going to talk about very soon. The third measure of central tendencies, mode, it's less used measure, but could be useful measure if you have a small number of possible values, the variable you are looking at. For example, if you look at the different occupation, there's a limited number of occupation, depends on how you classify, and then which occupation is most, that most people worked for example. Or if you think about unemployment, loss of jobs during the COVID-19. If you got the data, which occupation lost their jobs, if you got such a data, then you can plot and compute the mode of the number of the loss in the jobs. That might be actually useful measure. And which occupation is sort of the middle in terms of the job loss, for example. Okay. So this also is not affected by extreme value, as if you think about it, that it's sort of try to get the most frequently observed value, so that the changing the outlier value does not affect the mode at all. Okay, there may or may not be mode, because sometimes you have a multiple value line up in terms of the same frequency. Okay, so actually in this case, you can say there's no mode, and also you can say all values are modes. Okay. Yeah, so the you got more than two, you can say both are modes. Which measure of location is the best? Again, I don't think that there is no one single location measure in terms of central tendency. You like to, if you are serious about the data analysis, you always want to report the multiple measure of the central tendency. And then later we're going to talk about measure of variability or interquartile range, which tend to give you some sense to which how the distribution of the observation look like. And then those are the things that you have to do simultaneously. But mean is generally used, okay? But you have to be careful about, you have to ask yourself that whether there is extreme value could exist in the context or not. So the median is often also used because it is not sensitive to the presence of outliers. Okay. But if you are a data scientist, what you want to do is you report both and then get the idea. All right. Oh, okay. Here's a clicker question. Think about it. It's not that, how do I say that? It's a little tricky question because every year I do it and then the answer is mixed. So if you're willing, put your answer on the chat box. Oh, you guys look at the slides. So yeah, okay, then I move on. Okay, yes, answer is A. So the point is that skewed means that there is a tail value here, so that this has a really, really long tail. So that suggests that there is some observation far away on the left, so that the mean is going to be driven by those far away left values, and as a result, that mean is going to be smaller than median. Okay. Yeah, if you didn't look at the slides and get A immediately, I'm impressed, I should say. Okay, there are different types of different types of mean. So usually we think about arithmetic mean, but geometric mean is another important context in some contexts, like if you think about compounding interest rates and so on. Okay, so geometric mean is going to be, you're going to multiply the n value as a product and then take a root on n. Okay, power to 1 over n. Okay. So this is probably in a daily life, the most important application of this concept is thinking about financial investment, or you're gonna, in future, you might buy a house or a condo, and then you have to have a mortgage, and then you have to think about how much you have to pay. um, that's where that the interest matters. And then in order to think about how much you're going to pay in 10 years later, really, it's important to think about this geometric mean rate of return type of the computation. So here is a question. Okay, so suppose you invested $100 in stocks, and after 5 years, the value of stocks becomes $125. What is average annual compound rate of return? So I'm asking you without explaining what is exactly annual compound rate of return. So it's unfair clicker questions, but nonetheless, I'd like to ask. So obviously it's a trick question in the sense that I on purpose give A because 125 minus 100 divided 5 is 5. So I always hope that somebody is gonna answer it's A, but it's not, right? Yeah, so so I guess you might, or you don't know exactly which number is gonna be, but the argument is that there's a compound interest. So let's see. So that so 25% divided by 5 years equal 5% is not right, because you got the initial investment. If you actually get the 5% every year, then you should earn more than 100 at the end of 5 years. You should have more than 125, because there will be a interest you're going to earn in the first year if it's 5%. So that interest rate you earn is $5, and then there will be an interest on the interest you earn in the first year. So there's a compound interest. Okay, so if in fact the it is a 5% annual return, then you should end up getting 127.63 rather than 125. Okay, so the annual interest rate should be less than 5% to get that 125 after 5 years. Okay, and so it's important to realize that, and then the R has to be smaller than 0.25. And if you compute it, it's going to be about 4.6. Okay, this is very, very important for your financial investment. Okay, so if you graduate, you start earn money, you start saving, and then there's like a tax-free account, like a tax-free saving account, or if you start earning the money, then you can use so-called RSP, where you can that is a tax. You're not gonna be charging tax until you withdraw. So if you use those things, and then if you start earlier, like if you start saving like at the age of 25, say if you have like a $10,000 saving at the age of 25, and then average balance portfolio returns like a 7% in a tax-free account. And then after, you have to compute. After say 20 years, so you started from 25, after 20 years, which is 45. Still, you are in the sort of middle, right? Just keep $10,000 in 25 at the age of 25, and keep investing for 25 years in a tax-free account. You're gonna be surprised how much of the money you're gonna get. Do I have? Yeah, let me see if I can compute it. Yeah, I guess I have to, yeah. Okay. So this is my favorite website. Whenever I wanna compute something, I always use this place. At one point, suppose you got, I don't know, this conservative 6%, and you got 20 years, okay? So after 20 years, so you start from $10,000, it's gonna become $3,000. Oh, sorry, let me say. $10,000 to start from at age of 25, at age of 45, you get $32,000. So that it's gonna become more than 3 times because of this compounding interest, okay? So start early in terms of investment and so on. For mortgage, it's gonna go the other way, so you have to be careful. Okay. All right, so that is that, and then I wanna now talk about measure of variability, okay? So mean and the median is about where the location of the distribution is, okay? But as you know that different people have a different income, and the describing the data, if you can, is gonna be the drawing the distribution, okay? But distribution is very complicated object, so we like to provide some number which is easy to report and sometimes easy to compare, okay? So that's why we like to come up with the measure of location, which is a central tendency, and the measures of variability, which gives you the idea how much of the spread you have for the distribution, okay? So in terms of the, say, income, the spread of income means that there's an income inequality. In terms of wealth, spread of wealth means a wealth inequality, okay? So those are the important measures to think about policies and so on. So that not only the mean, which is a location, basically the location of the distribution, but also some type of the measure of variability, which is about how much of the spread you have in the data. Okay, and then we're going to consider different types of the measures of variability. Okay, so simplest one is gonna be just reporting the smallest value you observe in the data and the largest value you're gonna observe in the data. Okay, so that is called the range. Okay, in fact, that whenever you try to report so-called summary statistic of the some variable in the data, what you're gonna report often is a mean, median, and the minimum value and the maximum value. And that will provide some idea about the location as well as the where actually data lies. Okay, so this is a very, very simple concept. But range, as you can imagine, is going to be very, very sensitive to the presence of the outlier. Okay, so I think you want to be reporting a little bit more than the range in order to give the sense to which the how the data look like in terms of the distribution. Okay, so the disadvantage is going to be again about the sensitivity to the outlier. Okay, so in this example, also just look at down there. Okay. So this is a data set about, I don't know what the value is, but 1, 2, 2, 2, 3, 4, 5. Maximum value is 5, so that's a data set 1. But second data set, it's almost identical except for the last value, if the last value is 120. Then the range you're going to compute is going to be very, very different. So range is, again, very sensitive to the outlier, and then you have to be careful because sometimes the data has a miscoding, and other times that inherently there are very many, some small fraction of the observation taking very high value, and that will not provide the where the body of the observation lie. So for this reason, we want to start thinking about presenting more better information in the distribution, in terms of the distribution where the data lies. Okay, so and then there is a so-called interquartile range. And this type of box plot is very, very useful for visualizing the data, and often people use it with different percentiles sometimes, but interquartile range is very useful to think about the presence of outlier, as well as where the most of the observation lie in the middle. Okay, so what is the idea behind the interquartile range? So you can always rank or order the value of variable x, okay, from the lowest to highest. And then you're gonna split this observation into 4 groups. First group is gonna contain the 25% observation, and then among those value, the value is gonna be among the lowest, okay? And then the second group is gonna be the second lowest, and then the third group is second highest, and the last group is the highest group. So you split the observation after sorting in terms of their values, and then look and then split into the 4 group in terms of value. And then between the second group and third group, there is a median, okay, because you are ranking the value of x here. Okay? And then the interquartile range is about where the second and the third group, namely the middle group, is gonna lie in the data, okay? So the second group, the lowest one, takes the value 30. The third highest group, third group is gonna have a highest value of 57. So that is corresponding to 75 percentile value of the observation. So you got the 37 as 30 and the 57 as the 25th percentile and the 75th percentile, and then between these two gives you the interquartile range, okay? So presenting the number like 27 is also good, but why not just present visualization like that? That gives a pretty good idea about how the data's distribution look like, especially if you get used to watching this type of graph. And also that you can get a sense to which the outlier present there or not, because that if this has a longer length, that means that the extreme value is present. Okay. So what does its interquartile range tell us in data? Well, that is actually tells you the variability of the data in the sense that if this is large, that means the spread of the distribution is going to be more. Okay, so you compare these two distribution. The first one is not spreading. The second one is spreading, right? So if you compute the interquartile range, the first one is very, very small, but second one is going to be larger, okay? And furthermore, I'm not sure that if I'm going to talk about this or not, but sometimes interquartile range provides a robust way of computing standard error, which I'm not sure if I'm going to talk about it or not, yeah, so that is formally you can connect to the concept of standard error under the assumption that normality is a good approximation. Yeah, so it tells the spread in the 50% range of data given in the middle part of the distribution. So that is, you have one extra qualification on the middle part. Okay. So it's a very useful. Okay, so here's an example. So state an example. I should change to R example soon, maybe. So this is about the distribution of the final grade in the past, among the past students who took Econ325, the last like 5 years. And then I classified between the low homework group and the high homework group. High homework group tend to have a higher final course grade, okay? And then how that distribution look like? Well, I can always plot the two distribution, but the box plot like this is also helpful, namely in the high group, the middle 50% of the students get between 65 to 85, 70 to 85. And then the low homework group, those who don't complete homework tend to have middle part of the guys tend to have between below 40 to at most 60. Okay. And then that if you don't do well in the homework, the maximum value is 80. Okay, right? So, I mean, this is very, very, I think a nice summarization of the data. So if you ever become a data scientist to analyze the data, so, you know, a lot of times you want to compare two different groups or two different treatment groups. The first thing you do is going to be you do something like this to compare the two different groups and how distribution is going to be different. And then this type of the interquartile range box plot is very helpful. You can do a little bit more complicated things by thinking about the more complicated data. So this is the data about evolution of the growth rate of deaths across US states. So there are like 51 states in the US. And at each point of the day, okay, so if you think about like April 1st, you got a data about the growth rate of deaths due to COVID on April 1st, okay, weekly growth rate around April 1st. You have the data like that. So on that data, you can always construct the, this type of the box plot, okay? But we like to plot that information over time. How am I gonna do? I am actually computing the 25 percentile and the 75 percentile of the growth rate across 51 slots. If you look at the 75 percentile, it's gonna look like that. 25 percentile is gonna look like that, okay? So this is gonna be an extension of the idea about how to present the, where the main observation, the area is gonna lie, okay? You can add other percentile like 5% or 95 percentile, okay? But at each point of time, you can construct the box plot like that, but you wanna see how the distribution change over time, plotting the time series of each state's growth rate, and then compute each day you can compute the interquartile. Okay. This is a similar things. So this is coming from so-called Google Mobility Report about Google make it publicly available about some measure of the transit intensity across different US states, actually across all over the world, okay? so that we have a corresponding number for the BC or Alberta, the Ontario, and so on. But here I'm gonna try to see that how much of the people's mobility reduced after the COVID, and then they recovered during the started to reopen. Okay, so this is essentially they look at they have a GPS data about how frequently and how long each individual spend time at the transit, like a public bus, public transit like a bus or trains. Okay, and then there's a 51 states, so that depends on which states, how much of the reduction. So this is like the zero means compared to the January of this year, okay? Compared to the January, say the bottom part around this, in April, many of the states, transit activity is really low, okay, below 25%. And then some states, like New York, I guess, is going to be really, transit is even less, so that there is a more than 50% reduction in the transit, okay? And then gradual recover, but of course that depends on which states. You know, some of states do not affect it much. In April, then that they don't change the movement as much, okay? And then you can actually do the same thing. So this is again, it's actually quartile. So this is a 25%, it's missing the quartile number, but it's a 75%, 5%, 5% and 95%, okay? So presenting this gives you some, gives you some idea that how the transit intensity change over time. Yeah, so there's one question, why there's some drop like this at some point. Okay, so this is a daily data. So what do you think, why we have a drop in the, yes, weekends, that's right. Saturday, Sunday, people do not take as much of transit because they don't go to work. Okay. Actually, this is actually important points if you are doing data analysis. So you have to be careful. By plotting this, you actually immediately realize, of course, it's holiday, so that people don't use as much of the bus or trains, okay? What's that supposed to mean? Well, if you're trying to analyze that, you have to take into account of that. So visualization is very important to understand what we have to do when we analyze. If we do any analysis using this data, we have to take into account that we have like weekend effect. So you can add weekend dummy, or in this case, you can actually take the 7 days average so that you can smooth the weekend effects. Green line and this green line is 25, red line is 75. Okay. And then at the bottom is 5%, and the highest one is 95%. Okay, so those are just an example. But I mean, I'm not teaching any programming here, but understanding when you start learning programming, maybe by yourself, understanding the importance of visualization, how you can visualize is important, because you notice something you have to take into account when you do data analysis. All right, so we are talking about range and the interquartile and how you potentially can do visualization. But that's not the only measure of variability. In fact, the more popular and the traditional measure of the variability is variance and the standard deviation. So let me explain about what is variance and what is standard deviation. Okay, so population variance is going to be about the one measure of the variability, which is the average of squared deviation of values from the mean. So that's what it is. Okay, so what is it? So look at this term. Okay, so I guess some of you already taken look at the lab session, but I have to explain a little bit about the summation. So what this summation means? Well, that means you are actually summing up x1 minus mu square, x2 minus mu square, x3 minus mu square, and so on. So you got the n different observation, x n minus 1 mu square plus x n minus mu square. So, so often in the computer programming, you're gonna do computation like that. You're gonna sum up across different observations. If you wanna do it, write a program by yourself without using any package, you can actually do sometimes a do loop to compute this type of the value, okay? But writing up this type of the long summation is time consuming. So we introduced a notation that represents this a long summation across different units, okay? So that's a summation operator, okay? So we already had it when we discussed, I skipped and I didn't talk about it much, but if you wanna go back to even the average, this summation operator means that you got the different units. So there's a person 1, person 2, person 3, and so on up to nth person, okay? And then you wanna take average, what you're gonna do, you just sum up across different units and divide it by L. Now writing up this summation is a little time consuming and long, so we often use this convenient notation, summation operator. So it's just a short-handed way of writing out the sum across different units where subscript I is going to represent each unit. Okay. Summation operator is something you're gonna repeatedly use in this class. You have to get used to, and you will get used to for sure, okay? Because you're gonna go through a lot of exercise using this summation. But it is very confusing, okay? As simple as this, you don't get confused. But sometimes you got the double summations, and sometimes you got the product of the variable where you have a different subindex of the I and j, and then in front there is a double summation, like you're gonna sometimes have notation like, hey, yeah, maybe you have an exercise like that. Notation like that. Once you have a double summation like this, you start confusing. And you do, huh? So you have to remind yourself what this summation operator means. For example, in this case, you can keep outer summation. Namely, you just fix that value of I, okay, and then open up the value in terms of j, so that you fix I, and then y1, xi, y2, xi, y, and x, okay? So whenever you have a double summation, that until you get used to, I recommend you sometimes you actually open up to make sense that what this double summation means and so on. Here, key point is that you got index of n changing, while index of I is fixed at I. or going back to the definition of the variance. Okay, here you go. Okay, so the variance is defined as average of the square of the deviation from mean across an observation. Okay. Why am I doing this? Well, that's the quadrat, sorry. So the quadratic measure, so in order to measure the spread, you somehow have to measure the deviation from the center. Okay, so the spread is about how far on average that each observations are going to be away from the center. Okay, and in Euclidean space, the squared distance is a very, very useful and well-used measurement of the distance across between 2 points. So we are looking at the points x1 and the point mu. Okay, so you think about some distribution. There is a center mu, and then you think about the value x1. So some observation is x1. You got the distance between mu and x1. How are we gonna measure? Well, the most commonly used measure is a square distance. So why am I taking a square? Well, one benefit of taking a square is that its sign is going to be always positive. So whether mu is bigger than x1 or x1 is bigger than mu doesn't matter. As long as the distance is the same, you come up with the same measure. Okay. So of course, that the square distance is not the only measure of distance in a Euclidean space. You can actually think about something like absolute distance. Why not? Well, there's example in terms of just measuring the measure of the spread. There's nothing wrong about using measure like that. Okay, that will gives you some idea about what is the average distance for each observation is going to be from the center. Okay, so that is, I think that is okay. If you're really interested in just measuring the spread, although that somehow for some reason, not many people use this distance. The flip side is that actually there is a good reason why people use this a little complicated measure of the square distance or average square distance. Partly because of the very important concept of the normal distribution, okay, which you have to wait later, but normal distribution is gonna, or in other name, there is another name called the Gaussian distribution. Of course, this famous guy, Gauss, first find out that distribution. So Gaussian distribution or normal distribution turns out to be very, very important when we study the probability and the statistics. And normal distribution is gonna be, the shape of the normal distribution is gonna be determined by only by the mean, which is the center, and then also the variance, which is a measure of the spread. So somehow that if you know these two numbers, you know exactly how the normal distribution look like for the particular case. Okay, and partly because of it, that the variance as a concept in probability and statistics plays a very, very important role. Okay, so in terms of the visualization, just try to get some measure of the spread. I think it's okay to have like an average absolute distance like this. But it turns out as we study more and more about the probability, it turns out that variance, studying variance, understanding what it is going to become more and more important. Okay. All right. Now here's another confusing point for now. Later you understand why we are dividing by n-1, but I talked briefly about that there's a difference between the population and the sample. And again, I don't fully explain here. Later, we're going to come back to this issue. So if you don't fully understand, it's okay. But intuitively, there is a population of interest, which is like all Canadian households. And then there's a sample, which you randomly draw a subset from the population. And that's the data set you have. And then using this subset of randomly draw the data set from the population, you compute so-called sample variance. Okay? Sample variance is going to be very similarly computed as in the case of population variance, except that there's a two differences. One, the mean is based on the data set you have in the sample, so that you're going to compute the sample mean. And the sample mean, we often denote this X bar. And this is a common terminology in probability and statistics. That's the first point. The second point, which is very confusing for now at least, is that we're going to divide by n-1 rather than n when we talk about the sample variance. Okay? The reason why we divide by n-1 cannot be explained now because you don't have a full knowledge of understanding why. Later, I am going to explain. So for now, somehow sample variance, in order to compute sample variance, you divide by n-1 rather than n, and then you keep wondering why. And then at some point, you have the right time to ask why you're going to divide by n-1, okay? All right, and then, so the variance is as a concept is important, but one difficulty is the unit. So you compute the variance given the data, and then you compute it. Whenever you report the summary statistics, you often compute it. And then you get some number like 25,552. Oh, that's a variance. Okay, so that's a big number, but how am I gonna make sense out of it? What's this magnitude of the variance means? Actually, it's very difficult to interpret the magnitude of the variance. You can always compare two distribution or two data set and compare the variance value across two data sets, and then you can say one is bigger than smaller. But how much and what's supposed to mean that the variance, one data set's variance is 500 and the other is 10? What that's supposed to mean? Well, they have to interpret the magnitude. Turns out it's very difficult to interpret the magnitude. Why? This is because of this square. Okay. So as I said, okay, let me actually clean up a bit. So as I said, variance is going to be a average square distance. And as a result, all right, so there's a one chat question. So variance is unit free. That's a very good question. Think about it. Okay, suppose we are computing the variance of the household income across all Canadian households. Okay, so you got the unit of X being the Canadian dollar, right? So what is the unit of the variance then? Anyone willing to type? Canadian dollar, is it the case? What about the square? If we take a square of the, dollar square, but what's it supposed to mean to have a dollar square? Well, it doesn't make sense. I don't know how to interpret. So the unit of the variance is dollar square. So we can, it's hard to interpret. Oh yeah, great. So you suggest take the square root, exactly. That's the concept of standard deviation. Okay, so the variance itself doesn't make sense because its unit doesn't make sense, and then how I'm gonna interpret the magnitude, well, I don't know. So, okay, so I'm gonna take the average of the square distance. That gives a variance, but that itself doesn't give me any interpretation. So shall we just take the square root? Exactly. That's the concept of standard deviation. Okay. So this standard deviation makes sense in terms of having the same unit. Okay. And it turns out, so this is getting back to this normality, or the distribution of normality. This standard deviation turns out to be very nice concept to use. Once you get this value, you actually get a good idea about where the mass of the observation lie. Okay. In particular, you take a if you take two standard deviation away from the center, if the distribution is approximately normal, that's going to contain about 95% of observation approximately. So that standard deviation gives you a very good idea where the most of the observation lie around the mean. Okay. We get back to that later. Okay, again, there's a distinction between population and sample. For now, I cannot get into too much in detail, but later we're gonna get. So the sample standard deviation is gonna be computed with the, based on the sample variance. Yeah, again, you're gonna divide it by n-1, and then you're gonna use the sample average. So example, suppose you got like 1, 2, 3, 4, 5, 6, 7, 8 observation. If you compute me, turns out to be it's 16. So how am I going to compute a sample standard deviation? So first, I have to compute that for each observation, I have to compute the square distance from the center of the sample, which is 16. Okay, you do that for the first observation. You do that second observation, so on. Take the sum and divide it by take the pseudo average, I should say, n-1 and n. And then compute the variance inside. Variance is 126 divided by 7. And then take the square root, that gives you 0.2426. So that is the measure of the spread, okay? How useful it is, I'm gonna explain later, hopefully. All right, so measuring variation. So we just try to get a sense that how the distribution of the data look like by summarizing it in terms of some number. That's where interquartile range is useful. That's where the standard deviation is useful as a measure. So you can compare standard deviation, and then So suppose you have a 3 data set, data A, data B, data C. So turns out that this example is constructed so that the mean is going to be identical. If you look at just the data, so this is just so-called empirical distribution or frequency distribution. You get immediately that the data B is going to have a less of the spread, and then data C is going to be more of the spread. Okay, and then if you compute the standard deviation, you can confirm exactly the number. Okay, but for now, you don't get how exactly you're going to consider that what is that to say the standard deviation become being 4.5 versus 0.9. You don't fully get it. But one hint I can give, which hopefully I'm going to have a slide soon, is that, for example, if you think about here, data set B, center is 50.5 as you see, and then you're going to think about the twice of the standard deviation. So 1, 2, 1, 2, okay? So if you take, starting from the middle and take 2 standard deviation away on the both sides, okay? It's going to be here. And that's going to contain almost all observation. Okay, you can do the same thing here. Mean is here, so you're going to have twice of that, 4.1234.5. So twice is going to be actually far away, but 2 standard deviation gives you, in this case, all observation included. The same here. You got here 1 to 3.5, so that 2 standard deviation cover turns out all observation in this context. So somehow it turns out the 2 standard deviation away from the mean on a bigger side and smaller side gives you some idea where the most of the observation lie. That's where the concept of the standard deviation is most useful at this point. Later, it's going to be more useful once you start learning about the hypothesis testing and so on. But just simply knowing 2 standard deviation away from the mean, you compute, you get a good idea where the observation is. So it's magical. It's like a magical. You only report 2 number, mean, standard deviation, and that's what you actually see in the newspaper and the magazine whenever they report some information about some survey data like presidential election voting and so on. They often report not only mean, and recently they often report the standard deviation. How are you going to interpret? Well, you can immediately start picturing where the data lies by taking 2 standard deviation away from mean. So advantage of variance and the standard deviation, well, each value in the data set is used in the calculation. Well, that's advantage, but also if they exist outlier, this could be a disadvantage. Values far from the mean are given extra weight. So that's, oh, actually, this is an important point. Right. So when you compute the variance, right? So when you got x1 equal to 1, x2 equal to 3, x3 is equal to 4, and then the x4 is like 100. Well, 100 is not good. All right, now let me give you one more thing. Like 5 is minus 100. So the average is going to be like around 2 or so. Okay. However, you compute. What is average? I should have come up with the easy example. So let me actually get the easy example. I'm going to make it easy. Okay, so suppose you got the 5 observation, minus 1, 0, 100, minus 100. In this data set, average is 0. Okay, what about the variance? Well, variance, well, in this case, it's sample variance. So let me actually use, okay. How am I going to compute? Well, I'm going to compute square. Okay, so that's how you're going to compute the sample variance. But note that this part of 100 square, well, 100 is much bigger number than like 1 in terms of magnitude, deviation. But you notice that you're actually going to square it. So when you compute the variance, the outlier or extreme value is going to have a huge impact on the variance as a value because of the because you're going to take a square, right? So that is a sense to which that variance as a measure of the variability per se is sensitive to the outlier. Okay, so that's a disadvantage. Somebody asked in a chat that the unit-free measure. Well, still the standard deviation itself is not unit-free because the original unit is preserved, and that's on purpose. That's actually an advantage. But in some other cases, if you want to compare the distribution across two different variables with different units, is there any way to construct a unit-free measure of the spread? So that's where this concept of coefficient of variation comes. Okay, measures relative variation, and it's always percentage show variation relative to mean. What is this? Well, so you got the standard deviation as a measure. So if you start from the dollar, so if you're computing the standard deviation of the household income, the unit is dollars. You divide it by the mean, sample mean, which has also the dollar unit, and then dollar unit is going to be canceled out. So that the coefficient of variation that is defined by the ratio of the standard deviation to sample mean is going to be unit free, okay? And then this is a useful measure in the sense that you can compare the distribution across two variables with different units. Okay. So here's one example. When you invest financially, the stock has its own unit price, but unit price itself is not so important because sometimes they change the unit and the splitting the units on the margin and so on, so that the unit price itself is somewhat arbitrary, okay? So in order to compare the two stock price and then how they varied over time and so on, that you have to somehow normalize. And then this is the one way, the coefficient of variation is one measure you can use to normalize, to compare how variable the stock price is across stock A and stock B, okay? Because it's gonna represent the percentage deviation from the mean. So that, which is more risky? Well, suppose stock A's unit price is $50 and the standard deviation is 5. Average price is 100 and then standard deviation is 5. And then you can immediately get a sense to which that the stock B is less variable because the high average price, however, that less of the standard deviation. Okay, so that you can confirm by computing the coefficient of variation. All right. For the rest of the 2 minutes, I'm going to talk about empirical rule and then the class. And this is very important. Every year in the midterm, you're gonna see the exam question on this, okay? I now say that. So you should study this, okay? And you remember, even if you forget about everything else about this class after 10 years because you don't do any statistics, but I hope you still remember this empirical rule. And I think you remember. Okay. So empirical rule tells you that if distribution of the observation is approximated by normal distribution, which we haven't discussed yet, later we're gonna study a lot, then the standard deviation gives you a lot of information about where the observation lies. If you take the one standard deviation around the center, then if the distribution is approximated by normal distribution and the mean of the observation turns out to be approximated well by the normal distribution, then the one standard deviation away around the mean gives you about 68%. What's more important, I think, and then this is something you're gonna remember after 10 years, is you see the standard deviation reported, and you see the mean reported in the news magazine, and then you immediately picture this graph and then get a sense that, all right, once I know the mean, once I know the standard deviation, take the two standard deviation away from the mean, bottom and the top, then you got 95% of the observation. If you take the three standard deviation, almost everything is included. And then I'm gonna finish with clicker question, okay? Suppose you have an average stock price of Google was $8,800. That's actually, I get from the actual data a few years ago. And then suppose the standard deviation equal to $100. What is the approximate interval? Approximately 95% of stock price will be after 1 year. Oh yeah, everybody got B. Yeah, how do you know that? Okay, so those who answer B was listening to me, okay? So it's a $200. So standard deviation is one, you're gonna multiply by two, it's a 200. So you're gonna take 200 less of 800 or 200 more of the 800, that gives you a 600, so the answer is B. Yes, plus minus 200. And this is a question you're gonna see in the exam, okay? At least in the past 4 years, every time I write midterm exam, I come up with a slightly different exam question like this. It's a bonus question because everybody will get it, okay? And okay, so that's it. I'm gonna talk about the rest in the next class and then move on to the lecture 2. Make sure you're gonna finish the clicker question on the Canvas, and thank you for coming to my lecture, and thank you. No, it's not due today. Due is gonna be anytime before midterm probably. But before you forget, you should do it because sometimes the questions are not gonna be complete. You have to refer to slides if you forget about what they are. So you should do it before you forget. Okay, is it all right to just scan my paperwork for us? Yes. Oh yeah. When we compare two coefficients, that's okay. So in terms of first one, so you can scan it. What's I I have my favorite app. You don't necessarily use uh you don't necessarily use it, but I like Cam Scanner. Professor, when we compare two coefficients, does we talk about more sensitive or less sensitive?
Yeah, if it's related to the prices.
What do you mean to say sensitive?
For example, our example, CVA and CVB. The first one is 10%, the second one is 5%. So can we say the first one is more sensitive than the second one related to their prices?
I guess what you means, I think you meant to, I sort of understand what you're trying to say, but we don't use the sensitive as a word to describe that. It's, I'm gonna say, more variable or more uncertain. So as an investor, you try to think about which stock you're gonna purchase.
Yeah.
If, and then if the average return is the same, I'd like to pick the stock that has a less variability. And then that's how you're going to measure the variability across different stock. Coefficient of variations help you to get better understanding about how sensitive is. I'm using sensitive. How variable that, how uncertain the future price is.
So we
But
call it
yeah,
uncertain. So which one is more uncertain? You mean the stock B or?
stock A, because it has a higher standard deviation. In the
Higher
future,
standard deviation. So it's
right.
more uncertain.
Yeah, right.
Oh, I
And more
see.
risky. How, whatever you say, it's a more risky stock.
Yeah, more risky. Thank you. Yeah.
Yeah.
Make a note. Risky.
Okay. You don't have any other question, I'm gonna finish.
Yeah, have a great day.
Yeah, you do. Bye.
Yeah, bye.